So welcome everyone to SESE Colloquium for March 3rd, 2021. Today is one of our new traditions. I think this is the third time we're doing this, of having some of our graduate students give presentations about their work. We have three great grad students today. And our format is going to be that each will be introduced briefly by their mentor, their lead mentor. They'll each give a presentation of about 15 minutes, leaving about 5 minutes for questions. And then we'll do one at a time, one after the other that way. Ed and Greg and John, if when you're down to just a minute or two left, I will turn on my camera and hopefully you'll see me, and that's your sign that it's time to start winding up if you haven't already. So without any further ado, first of all, there's no announcements as far as I'm aware from Ramon or Minnie, so we're just going to go right into our talks. And without further ado, then I will turn it over to Evan, Professor Scantiaco, to introduce Ed.
Okay. Thank you, Professor Anbar. It's my pleasure to introduce our first speaker, Ed Buie. Ed came to SESE from Michigan State. He's actually the first in his family to go to college, and he started out as an accounting major, and then he took a course from Megan Donahue, the former president of AAS, and decided he wanted to be a scientist. So within 3 years, he retooled his whole undergrad study, and not only by the end of it, he was doing graduate courses and done research. So Ed is not afraid to sort of chart a new direction and figure out how to get there and put in the work to get there, which is a very SESE thing, I think. And he's done a lot since he's been here. He started collaborations with at Hamburg and with Durham University in the UK, and he's contributed a lot to the SESE at home. So he's been president of the Grad Council. He started a series of workshops to fight sexual harassment, and he's on the Jedi Task Force, amongst other things. And I could go on about him, but I want to leave plenty of time for him to talk about the fun research that he's doing. So without further ado, I'll turn it over to Ed.
All right. Well, thank you, Evan, for your introduction. Hopefully people can see the talk here. So thank you all for coming today. So my name is Ed Buie II, and I'll be talking about turbulence in the halos of galaxies. To the right here, you're seeing a simulation movie from one of my simulations, Play Forward in Time, we'll get more into. And thank you to NSF for sponsoring this research. First, before we get into things, I want to acknowledge all those who have been negatively impacted by the COVID-19 pandemic, and in general, anybody that's just going through anything. And thank you to all the essential workers for their efforts. We will get through this. So to talk about the scales I'm interested in, we got to start from something people are maybe more familiar with. So the solar system, with the recent news of the Mars rover getting there, congrats. And so here's a figure of the solar system. And if we look at this is not showing the relative distances, but the scale bar on the bottom is. If we look at the distance from the Earth to the Sun, it is what's defined to be an astronomical unit, so 1 AU. And now if we were to look at the total distance of that solar system out to about the edge, what we call the Kuiper belt, this will be about 156 astronomical units. To put that in context, that is about 4.5 billion miles. So it's pretty big. But of course, we can zoom out and go bigger than that and look at other stars around our sun, right? There's more stars out there. And so we can look at a stellar region around the sun about 15,000 times bigger. And of course, now that we're going to these bigger scales, astronomers, we got to make up more units because we don't feel like saying, million or so AU or miles. So we call it light years. So this stellar region is about 30 light years across, where a light year is the distance traveled by light in 1 year, because light travels at a constant speed. Of course, we can get bigger than this, though. And we look at the entire Milky Way galaxy, right? Where you have this collection of stars, gas, and dust all kind of spiraling together. And again, moving up to bigger scales, so we got to make up a new unit for this. This time, the kiloparsec, where the Milky Way is about 30 kiloparsecs across. So Milky Way is cool. Galaxies are awesome. A lot of cool stuff happens there, but I go even bigger than this. And so I look at something called the circumgalactic medium. This is the gas around galaxies, and it's very important in regulating how that central galaxy evolves in time. From the scale bars, you can immediately see how much bigger it is. It's about 20 times bigger than that host galaxy. And a lot of things happen in this gas. We have outflows from various star formation happening in that galaxy. As massive stars go supernova, they explode and send a bunch of energy and material out into this outer halo where it can mix and further recycle with that gas there and eventually rain back in on the central galaxy. You also have gas accreting from outside of this circumgalactic medium, uh, gas from the intergalactic medium. And then in addition to that, this gas is diffuse. On average, if we were to look at a meter box of particles in this gas, on average, there would be about 100 particles in that box. If we compare that to Earth, that is about a trillion times less particles. So much less stuff is as far as like how far apart these particles are is very far apart, but they're very a lot of interactions happen here, a lot of stuff is happening here, and we want to understand this. So, but how do we even observe this gas if everything is so far apart? Uh, so astronomers are kind of kind of crazy. We looked out into the space. We saw these things called quasars, active galactic nuclei, these giant laser jets that extend from the central galaxy and most times are bigger than that central galaxy. As technology got bigger, we can zoom in and find out like, oh, it's a supermassive black hole in there. And it's putting out all this energy. These things happen to be the brightest things in the universe. So why not use these bright lasers to detect stuff? So that's what we did. As those bright sources of light are on their way to us, they might interact with gas in the way. That gas will absorb some of that light from that quasar, which will allow us to know what is in that gas. And so here I'm showing a bunch of surveys on the right that have looked at gas around these halos with these pencil beam-like measurements. On the y-axis showing the absorption. So high values is a lot of this ion, and then low values is not a lot. And then close into the central galaxy, and then further out as we move to the right. So this first panel just showing hydrogen, neutral hydrogen, hydrogen with all of its electrons. We see it all the way out. Hydrogen is the most abundant element out there, so we expect to see a lot of it. We go to magnesium too, on the other hand. There's not as much magnesium in the universe. And it doesn't take a lot of energy to remove one outer electron from magnesium. And so this traces stuff that is closer in to that host galaxy. You don't really see it too far out. We can go to hotter stuff, look at something called oxygen 6. This is oxygen with 5 of its outer electrons removed. It takes a lot of energy to do that. And so we see it kind of all the way throughout. And so observations like these help to inform a picture of the circumgalactic medium of like a diffuse fog, almost hot fog with small clouds throughout of cooling material. And so I wonder if such a situation could be explained through turbulence, a feature that involves the mixing of cold and hot material, which is exactly what will happen in the circumgalactic medium. And the answer is yes. When I first got here, the simulations that I did were these 3D box simulations of the gas of this circumgalactic medium gas. But these were a much smaller scale. So it was akin to looking at parts of this halo. And so I was stirring at a constant rate throughout this box and the special thing about this model is that it uses non-equilibrium chemistry. This means that the ions and the chemicals they're able to evolve in this gas are pretty much allowed to go in whatever states that they might go, depending on the temperature and how much stuff is there. A lot of models, they don't have that non-equilibrium chemistry because it takes a lot of time to run those models, but that's the special thing about these models. And so this taught us a lot, but of course we can do better. And so now, scale things up, we look at the entire halo. We started such that most of the matter is concentrated to the center. You see this little white scale bar showing the disk of the Milky Way galaxy for size scale reference. That would be in the middle there. I started all at some same constant temperature. In addition to the turbulence, I made some adjustments to the turbulence so that the stirring is strongest in the middle. I'm trying to investigate star forming galaxies where the energy generation is strongest in that center part. In addition to that, we got rotation and magnetic fields in here, which are going to influence the motions of these particles and how it cools and heats. And then a black ring just showing kind of the area of interest for the stuff that I'm interested in. And so we stir it around and we come back 5 billion years later and it looks very different. You can see kind of this face-on view, this top-down view if you're looking at it. You can see that spiral structure kind of form. And then from the side, you can see how that disk looks. And the great thing about this is that the turbulence is able to set up this convective flow in this hot halo where the hot gas is able to move outward and be replaced by cooler inflowing material. And what that looks like is like this, where I have two movies going, on the left showing the density where stuff is, and then on the right showing the temperature, how hot and cold that stuff is. And we see as we move forward in time, stuff kind of falls in the center. We have this pressure wave moving outward that kind of disperses matter further out and heats it up a bit. And then we see this extended disk of material form. Um, and the interesting thing is that if we look at the Milky Way disk, this is much larger than the observable, Milky Way disk that we think of. And this is something we see in reality where we see galaxies have this extended disk of stuff around it. And people in CC research now, like Mansi Padave. In addition to just how it evolves in time, I'm also looking at the magnetic field growth. And for this plot, I am showing magnetic field evolution on the left and on the right, also showing that evolution, but this is only plotting the magnetic field not in this white circle. So I'm taking out all the magnetic field values in this circle. Like I said, I'm interested in the gas around that galaxy. And you see that it peaks at about 500 million years. And then after that, it steadily decreases and kind of gets to some constant value and then decreases again and gets some constant value and then goes down again. And it's interesting because I don't really know why that happens. I did not necessarily expect this. And it may be a function of density. Magnetic fields grow because they're being moved around a lot. Magnetic field lines are being twisted up and they don't like to be manipulated like that. And so you need matter to amplify the magnetic field. And as these simulations are going forward in time, that matter is cooling towards the center. Some of it might go inside that white circle, which means that I'm not counting its magnetic field contributions. And so there's less matter overall in that gas around it. But I have to plot the density versus time to see and make sure that's what's happening, because it might be something else. Also, that extended disk of gas is supported by the magnetic field. In the right, I'm showing something called plasma beta. This is the ratio of thermal pressure, pretty much getting at how hot that gas is, to magnetic pressure. And we can see that this extended disk of gas is pretty much mainly dominated by that magnetic pressure. You see smaller values to the white seen in that extended disk of material. And that's interesting because that magnetic field presence in that extended disk might have an influence on how that gas behaves, how it cools, how it heats. And these are more things I need to investigate. These are all very new results. And of course, simulations are awesome, but we got to compare it to some data to make sure we're on the right track. And so here I'm showing neutral hydrogen from 3 different simulations this time. The red or pinkish red simulation is what we've been looking at, magnetic field plus rotation. The green is rotation only, so no magnetic field. And then blue is magnetic field only, no rotation. And then the black are data points from recent Hubble observations a few years ago. And then, of course, x-axis is a function of distance away from that central galaxy. And all of these profiles look fairly the same. They all overlap with each other. They match with the data in line, which is good. These simulations are on the right track as far as matching observational features. The interesting thing, though, is that we don't notice any real difference in that neutral hydrogen close into the disk between things, rotation only that has no magnetic field and the ones with magnetic field. So I'm not sure, yet how much of a difference that magnetic field in that matter changes things, but it has to do something to it. And then, of course, if we don't consider the magnetic field, we see a lot more neutral hydrogen further out. The magnetic field kind of limits the amount of mixing that can happen, which gets you that neutral hydrogen. And then we have some ion ratios. There's a lot here, so I'm going to walk through it slowly. On the y-axis, I'm showing silicon-4, the ratio of silicon-4 to oxygen-6. That's 3, so silicon with 3 of its outer electrons removed, oxygen with 5 of its outer electrons removed. On the x-axis, I'm showing nitrogen-5 versus oxygen-6. So nitrogen with 4 of its electrons removed, oxygen with 5 of its electrons removed. And then I'm showing the magnetic field and rotation case. The diamonds, squares, and circles are Hubble data. The colors of them don't really matter too much. And then the red stars are data for my simulation, or sight lines for my simulation. Uh, the blue line or cyan line is showing a equilibrium model, and we can see off the bat that that equilibrium model, where the chemistry and ions aren't allowed to um, to venture into all of their states in regards to like temperature and the density in that area, it doesn't match the data. It's to the right of the data, and so if we consider that non-equilibrium chemistry with the gray line, it is more in line with the data, but the gray line only considers a certain type of cooling called radiative cooling, where stuff just emits light. Everything emits light. You and I, we're all emitting light. We're emitting infrared light, so we can't see it. Uh, but my simulations, they include collisional cooling, so stuff colliding together and releasing energy. And we see that that mixing is able to match the observational data much more. So just to conclude, galaxies have an invisible halo gas surrounding them called the circumgalactic medium. This medium is important to how that central galaxy evolves. It's where gas is recycled and gas flows outward and inward. Turbulence allows for the cycling of that hot and cooling gas. And we saw that the magnetic field rose steeply and decreased slowly in the halo of time. This might be a consequence of the density profile in that halo over time, but that's something I got to look at more. We saw the extended magnetized co-rotating disk of gas there. And we also saw that non-equilibrium chemistry produced neutral hydrogen profiles and various ion ratios that were able to match the observational Hubble data. So thank you. That's all I have. And I'll take questions.
Thanks. That was awesome. Beautiful, beautiful modeling, and you were right on time.
Oh, awesome.
It's like you practiced it or something.
Hey.
So if you have any questions, just put them in the Q&A. We have one here from Kevin Trin. Why do we have a face-on and side-on a face-on and side view of galaxy evolution for different quantities, density and temperature, instead of using face-on for both?
Oh, I just wanted to show both of them. In reality, galaxies can be viewed from the side, just depending on how they end up for our viewing angle. So yeah, just to show what that looks like from the side. But personally, I think it's cooler from the face on to see that spiral structure. But from the side, we see that this little cooling clump of gas that's flowing around. You don't really see that in this slice through the center in the density. If we look at it from the face on. So that's an interesting thing that we can see if looking at this thing from different sides gets us.
Great. We got another couple of questions here. We got a couple of minutes still. Rosalie O'Brien asked, what's the significance of the ratios you showed in your second to last slide? AKA, why compare those elements specifically?
Mm-hmm. Yeah, so it's a great question. These are common, well, not nitrogen 5, but silicon 4 and oxygen 6 are commonly observed in these halos. Nitrogen 5 is too, but to a lesser extent. And so there's a big thing about these ion ratios gave a certain value and why that value is, and people trying to match this ion, that ratio. Now, special things about these ions is that the silicon 4 typically is found in the cooler gas along with neutral hydrogen, which might explain why there's so much of it. As neutral hydrogen emits light, silicon 4 can absorb that light or silicon 3 can absorb it and become silicon 4. Oxygen 6 and nitrogen 5 are kind of found at the boundaries of that hotter and cold material usually, where oxygen 6 is found along the boundaries as well as in that ambient halo itself. So this kind of gives you I would say these ratios kind of give you a insight as far as the structure of this halo.
All right, and then this probably be our last question. Steve Ruff asks, are the halos leftover material from the formation of the galaxy or material produced after they formed?
Okay, yeah, good. It's a mix of both. A lot of stuff was there, as galaxies starting to form. There's this, the notion of galaxies forming is called the bottom-up scenario. So smaller things come together and form bigger things. So the smaller things are bringing in their own clouds of gas. That gas is all still there, right? In addition, I talked earlier, sometimes you have gas coming in from outside of that. So it's a mix of both of these things. It's a collection, melding pot, if you will.
All right. Great. Well, thanks very much, Ed. That was fantastic.
Thank you.
And we'll now turn it over to Lindy. You should be able to turn on your camera and microphone and to introduce John.
Fantastic. Edward, thanks a lot. That was great. And Ariel, thank you for your completely masterful Zoom management, as well as for finding the speakers and lining it all up. That's a fair amount of work, actually. I really appreciate it. It's great.
Well, thank you. Appreciate it.
Yeah, well, I'm really happy to introduce John Morgan Christoph, who received his Bachelor of Science in Geology at the College of William and Mary and came to ASU for his PhD in Exploration Systems Design. John is deeply interested in asteroid resources, and for his PhD, he's studying the possible weathering and formation of a regolith on a metallic asteroid, something which has never been studied and is unknown what the answer is, in support of the SESE mission. So today, John's going to talk mainly about space weathering effects, but stay tuned for interesting research results of his on micro impacts produced by lasers into meteoritic metals, and also on the process of fragmentation, the many, it turns out, processes of fragmentation in meteoritic metals as the result of impacts. So thanks, John. Go ahead, it's all yours.
Thanks, Lindy. I think you've basically summarized my entire dissertation at this point. So I'm going to hit slideshow from beginning and then hit share screen. Okay. So yeah, as Lindy mentioned, here we're going to be talking a little bit about space weathering processes on metallic asteroids. And for those of you who are maybe not as familiar with, the missions that ASU is involved with in our department, in 2026, if all goes well, the NASA Psyche mission is going to be in orbit around main belt asteroid 16 Psyche. The mission's led by Lindy, which is why I'm working on this. So Psyche is interesting because we think it has a metallic composition based on the available evidence from ground-based astronomy. And that's a potentially very new kind of planetary surface. So as we're preparing for this mission, it's going to be vital for us to extrapolate the knowledge we have of the surface processes occurring on airless planetary objects like moons and asteroids and comets, and apply that knowledge to a new set of materials. If we're using iron meteorites as the analog for what a metallic asteroid might look like, we're talking about a wide variety of different kinds of materials, not just metals. The most common metal is a iron nickel alloy with two mineral types, chemisite and taenite. But also notably, there are accessory minerals and inclusion minerals that show up in this composition as well. The most common of those is troilite, which is an iron sulfide. And that's interesting because troilite is also an accessory mineral in other types of meteorites and on other asteroid surfaces that we've studied more extensively. So we can potentially use sulfide minerals as an avenue to understand how the surfaces of a metallic asteroid might be modified by the space environment over time. Now, as Lindy mentioned, there's a variety of processes ongoing on airless asteroids, micrometeoroid bombardment, larger scale impacts, but today I'm going to focus on space weathering by solar wind ion irradiation. So first of all, what the heck is that? So this is a multidisciplinary audience, so I feel it's important that we bring up the foundations of the field of study as well as the technical details. So for those of you who do not study space weathering, solar wind is the stream of low density plasma of hydrogen and helium and other nuclei of atoms that are emitted by the sun and radiate out into space at velocities of hundreds of kilometers per second. Now, the velocity is relatively high, but it's also worth noting how we actually talk about the energy of those particles. We use a kinetic energy measurement that is normalized to the atomic mass of the nuclei that are emitted. So as you can see here at the top, there is a hydrogen nucleus with a single proton, which has a mass of 1 atomic mass unit, and it has an energy of 1 kiloelectron volt. Below that, there is a helium nucleus consisting of 2 protons, 2 neutrons, and a single electron. It is singly ionized in this case, unlike an alpha particle, as some of the astronomers and nuclear physicists in the room might be more familiar with. And this will be moving out from the sun at a velocity of, or an energy of 4 kiloelectron volts, because it has an atomic mass of 4. So the rough composition of the solar wind is mostly the hydrogen ions, and there's about 5% helium with less than 1% of other ions like oxygen and carbon. But the thing that's interesting for our purposes is what happens when these ions impact the surface of an asteroid or an airless object in space, such as our friend 433 Eros here. Well, there's a diagram at the bottom right which shows a very oversimplified atomic lattice of a hexagonal closest packed structure. What happens is when these energetic ions hit the surface, there is enough kinetic energy that they will collide and potentially remove atoms from the upper surface layers of the material. This is a process called sputtering. Importantly, this doesn't just happen at the uppermost layer of atoms. These ions can penetrate through many layers of atoms deep and liberate ions from lower levels. Also, if there is enough thermal energy in the surface, ions from deeper layers can migrate up and fill the vacancies as these sputtered ions are removed. This is called diffusion. So what does this have to do with sulfur and asteroids? How does actually the process of space weathering modify these asteroids in ways we can observe? Well, it turns out because sulfide minerals show up in all these other asteroids and meteorites, there's been some study of this phenomenon already. There are three primary phenomena associated with space weathering on sulfides. First of all, depletion of sulfur. So there's a mixture of sulfur and some other atoms that make up a sulfide mineral. The sulfur is preferentially removed by space weathering, by ion irradiation. That's associated with optical darkening and reddening. If you look at the reflectance spectra as measured by telescopes or other spacecraft instruments of a sulfide surface, it will appear darker and redder than an unweathered surface. And both of these phenomena are associated with some microstructural neatness. So you can see here two images, one borrowed from a LPSC Lunar and Planetary Science presentation from 2013, and the other from a Nature Communications paper released last year. The one on the left is of a laboratory sample of a sulfide material that has been irradiated to simulate space weathering. The right images come from samples returned from asteroid Itokawa by the Japanese Hayabusa mission. And this is neat because this is showing us a comparison between what's actually being weathered on the surface and what we see in the replicating experiments in the lab. These, what they call iron nanowhiskers that you can see protruding from the sulfide surface, are the direct result of the sulfur being removed and the iron being left behind. It forms these nanoscale iron nanoparticles. So extrapolating this forward for our own purposes, what's left to know about this process? Well, we need to understand the contribution of hydrogen and helium ions distinct from other processes, because there's also thermal diffusion, there's also impacts, there's also micrometeor bombardments, and we want to make sure that we understand how each of those processes is contributing to the weathering that we observe. We also still have a bit of work to do to understand how the ions are interacting with the troilite surface from a fundamental sort of thermodynamics and physical chemistry standpoint. What's happening in those collisions is a bit more complicated than the simplified model I showed a few slides ago. We're also still trying to suss out exactly what this microstructure looks like, and more importantly, how does it evolve over time? There's many different sorts of phases and textures that we've observed in different return samples and lab experiments. So it's important for us to think about how those structures evolve over time. And then finally, this one is a particularly interesting piece of my own work is, can we identify a link between the observed spectral differences between weathered and unweathered surfaces and the roughening of the surface that's associated with the formation of those nanophase iron particles? This is something that's still very preliminary, so it's the most sort of speculative part of my work. But we've done a little bit of experimentation to try and get at these questions. So I'm reporting here a set of experiments that we performed in 2019, and we used two samples of troilite from two meteorites, Toluca and Canyon Diablo. They're both provided by ASU Center for Meteorite Studies. Thanks, Lawrence Garvey, if you're in the audience. We also performed experiments on a pressed powder pellet of troilite for comparison. And what's important to note here is that we're looking at both the polished and unpolished surfaces of these samples. So we have a very, very flat and smooth surface and a relatively rougher surface. And that helps us determine how the topography of the surface at microscopic and nanoscales influences the way that the weathering occurs. We irradiated these samples with a facility at the University of Virginia's Laboratory for Astrophysics and Surface Physics using 1 keV per AMU hydrogen and helium ions. And after irradiation, we performed a series of characterization tests on the irradiated samples. Presented here, not necessarily in the order that we did them, but in the order that we're presenting them here. First of all, to examine the chemical change, the sulfur depletion, we use X-ray photoelectron spectroscopy. This basically illuminates the surface of the sample with X-rays and then measures the energy of the electrons emitted by that energized surface of the uppermost few layers of atoms. And that tells us the ratios of the elements that are present and their chemistry. We use secondary electron microscopy to image the samples at very small scales so we can see how that microscale and nanoscale topography changes over the course of irradiation. We then use atomic force microscopy to quantitatively measure the roughness of the surface. This is a really cool technique, which I wish I had more time to explain in more depth, but basically you have a little probe that is a conical tip. At the tip of that probe, it's 1 atom wide, and you can poke across the surface back and forth and measure the exact height of your sample surface over a relatively small area. And that can tell you quantitatively how much height variation and how much roughness there is over your surface. And then finally, using instruments both at the University of Virginia facilities and here at ASU with Jim Bell and Stephen Dibb's group, we measured the visible and near-infrared reflectance of our samples to get the kinds of spectra that the SESE spacecraft might observe to see if we can determine how the various variables we've measured previously are related to what we'll actually observe when we get to SESE. Briefly, here's a table which shows the 4 irradiation experiments we conducted. The only important thing to note here is 2. First of all, we have a variety of different textures of polished surfaces, unpolished rough surfaces, and a powder surface. And also in terms of the fluences of ions that are present here, that is how many ions per centimeter squared of area of the sample we are bombarding the samples with. The important thing to note here is that we have a couple of radiations which use roughly solar wind ratios of 94 to 5% hydrogen to helium ions. And we have 1 irradiation just using hydrogen and 1 irradiation just using helium for comparison. So let's go through these results relatively efficiently. First of all, the X-ray data. So if you're not used to looking at these kinds of data, this can be a little overwhelming, but we'll walk through it. On the horizontal axes of these spectra here at the bottom left, you see the binding energy in electron volts. And the intensity is on the vertical axis. That is, how many electrons at each binding energy interval are we measuring over the course of the X-ray examination. And you'll notice that there are these peaks, which show electrons at various energies being emitted from the sample surface. Each of those energies represents the hybridized orbital shell of one particular electron energy level in the atomic structure of the atoms on the surface. And importantly, as those hybridized orbitals bond with the atoms nearby, they change slightly in energy. This is some Gen Chem 1 stuff. But you'll notice that that can tell us, for example, that some of the atoms of iron are bonded to sulfur, some of the atoms of iron are bonded to 2 atoms of sulfur, and some of the atoms of sulfur are just by themselves, just within the atoms that we can tell come from the sulfur. Looking at the iron data, we also see there are some peaks which show there are atoms of iron bonded to sulfur, atoms of iron which are not bonded to anything, and some atoms of iron bonded to oxygen. That represents the patina of oxide forming on the very surface layer of atoms because the sample has been stored in Earth's atmosphere and has had time to oxidize. You'll notice a couple of things from the spectra. One is that we have a lot more iron at the end, and we have about the same amount of sulfur, which tells us that there is a relatively higher amount of iron relative to sulfur, so sulfur is being depleted, as we expect. By taking the areas under both of these 2 peaks, we can quantify that ratio, along with several other elements. And on the right, we see that plotted for 2 of the irradiations that we've carried out. You'll notice that at low fluences, around below 10 to the 17th or 2 times 10 to the 17th ions per centimeter squared, we see that most of the surface is still dominated by that oxide patina coating. But after about 10 to the 17th ions per centimeter squared, we start to see the sulfide surface show through as that oxide patina is removed. So on the one hand, that makes a problem for us because we need to see what the sulfur surface is doing, not the oxide surface. So we did a little bit of modeling. This is a program called STTRIM-SP. Briefly, what it does is it simulates the kinetic collisions between incident ions and the surface of a sulfide over time. And you can see that as we plot the sulfur to iron ratio here on the right, it decreases as the amount of ions we bombard increases over time. Extrapolating that out to Psyche, which we can see here on the right, the ratio of sulfur to iron is decaying by this logistic function. And we see that it reaches equilibrium after about 10 to the third or 1,000 Earth years. That's important because that's a very, very short period of time compared to how long we think Psyche's surface has been exposed. So it's likely that when we get to Psyche, it will be fully irradiated and depleted of sulfur to equilibrium. So that's the chemistry. Let's briefly look at the electron microscopy and the roughness results. So these are some images taken with the Eyring Center's XL30 SEM. On the right here, you see a low magnification image showing the entire irradiated area is this bright sort of oval shape here. It's brighter because it's a little bit rougher than the surrounding material that's still polished. On the right, we see some higher magnification images of the Canyon Diablo and Toluca samples before irradiation at the top and after radiation at the bottom. Before irradiation, we noticed that most of the roughness on the surface is dominated by the scratches from physically polishing the surface. After radiation, we see that there's some roughness that's shown up. We quantify that roughness again using atomic force microscopy. And as you can see, we get some roughness. And importantly, this is the cool part, we only observe that roughness at nanometer scales, which is much, much smaller than the micrometer scale whiskers that we saw from the Matsumoto et al. Paper, and much smaller still than previous experiments, such as the Keller et al. Results from 2013. That tells us there has to be some other mechanism besides ion irradiation that is helping make these nanoparticles form, and that is causing these initial nanoscale particles formed from radiation to get bigger over time. Perhaps it's diffusion, perhaps it's some other process. We will have to resolve that later. I'm going to very briefly talk about the reflectance spectra, but basically the point here is we see the samples redden and darken as we expect them to. We don't necessarily see a correlation between the reddening and darkening of a spectra and how much weathering occurs either by chemistry or by roughness. Stephen Dibb and Jim Bell and I are still working those results up. Expect more details in a future paper. But so let's talk about the key takeaways very briefly because I'm a little over time. First of all, we quantify that on Psyche, if we have a troilite surface, it will likely be depleted of its sulfur after about 1,000 years. So we expect that any troilite on Psyche will probably be fully weathered when we get there. We also see a nanoscale sulfur depleted microstructure, again, much smaller than previously observed microstructures from other experiments and return samples. And finally, we see there's a link potentially between the sulfide spectra and the roughness, not just between the spectra and the composition as is traditionally assumed, but we're still working on that, so stay tuned. Finally, very briefly, let's talk about how this might apply for metals. We haven't done experiments on metals yet, so that's still to come. But even though metals are fully chemically reduced, and thus compositional change resulting from space weathering by ion irradiation is unlikely, that near surface microstructural change may still occur. And so that might also have a way of modifying the spectra. That's going to require future experiments. So again, keep us posted, but thanks for your attention. And I'm a little over time, so we'll keep questions confined, I guess. I'll let Ariel hand that though.
Great, thanks. Thanks for another nice talk. We have time for a quick question. Paras Angel asks, how can you tell the difference between space weathering caused by micrometeor bombardment versus solar wind?
It's a very good question, Paras. So the answer is it's complicated and we still kind of don't know, but that's part of the result that I'm finding with the only nanoscale structures resulting from the ion irradiation. One of the things that other scientists have found with micrometeor bombardment simulations is that they do see some of that microscale roughness and microstructure show up. what that might imply is that you need a source of heat to thermally diffuse enough iron to the surface layer to actually form the nanoparticles bigger than just a nanoscale structure, but that still needs a little more experiment to confirm that.
All right, great. In the interest of time, I think we'll move on. So thanks very much. And I will turn over to Patrick, Professor Young, to introduce our final speaker, to introduce Greg.
Hi, Ariel. Thanks for arranging this and giving students an opportunity to speak. I'd like to introduce Greg Vance, who has been working with me on his PhD. And I love working with Greg, but I'm proud to say he will soon no longer be my student. And he is interested in all manner of things related to supernovae, how they explode, and how they synthesize and distribute the chemical elements in isotopes. And I will not take any more of his time. So Greg, please go ahead.
All right. Thank you for the lovely introduction, Patrick. I admit it is truly bizarre to be introduced. I'm going to share my screen quickly. Give it a moment to kick in. And all right. So today I'm going to talk about supernova explosions, and I'm going to talk about all of the fun nuclear physics that happens on the inside. So I suppose myself and Patrick have already been introduced. I'll quickly shout out our collaborators, Chris Fryer and Carola Ellinger at Los Alamos National Lab. And without further ado, I'll get into it. So quick outline for the talk. I'm going to introduce core collapse supernovae for those of you who, maybe you're not so familiar with the subject, and we're going to sprinkle some motivation throughout that. Then I'm going to get into some of the work I've been doing on asymmetric supernova simulations, explain a few of the models I'm currently working on, show just a few preliminary results and some visualizations, and then there'll be a quick wrap up and summary. So let's jump into it. So stellar evolution is the general study of how stars are born, how they live, and how they die. And probably the most important factor of all, like number one for a star, is its mass. That is the thing that is going to determine the most of any number in stellar evolution. So it will affect the star's surface temperature, its brightness, its apparent color, the length of time that the star lives before it quote unquote dies, what its physical radius is, and ultimately, as emphasized in this talk in red at the bottom, we're going to be talking about the fate of the stars, and the mass is also the primary determiner of how a star is going to end its life. So if a star is above about 10 solar masses, which is 10 times the mass of the sun, then that star is going to end its life probably with a core collapse supernova. There are other types of supernovae, but we don't have time to talk about them today. So what happens in a core collapse supernova is that the core of the star runs out of fuel, collapses under its own massive weight to form a compact object, usually a neutron star or a black hole, and at the same time, the outer layers of the stars are violently blown off in an explosion that is honestly, based off of this image on the left here, quite beautiful often. This is the Crab Nebula. It's a remnant left behind from a supernova that happened quite a few centuries ago. So why do we care other than the fact that, exploding stars are really cool? So matter in today's universe looks, well, somewhat different than it did immediately after the Big Bang. About 13, 14 billion years ago, the composition of the universe looked a lot like this pie chart on the left here. It was about 3/4 hydrogen, about 1/4 helium, and the amount of elements heavier than that was pretty negligible. Today, the second pie chart I have on the right is the composition of the sun, which is not that different, but we've gone from heavier elements being almost entirely unnoticeable to making up 1 or 2%. And that 1 or 2% is important because that 1 or 2% of heavy elements being in the universe today is how we can have rocky planets like the Earth and all of the life that lives on the Earth. So, that's kind of an important step that the universe has taken to be able to bring about life so that I can give you this talk. This whole process of how the universe has changed over time is often referred to as cosmic chemical evolution. And one of the biggest players in this process is stars, and especially the supernova explosions of high mass stars. And they are going to fuse and create heavy elements inside them. And supernovae, in addition to fusing some of those heavy elements themselves, have a big task of dispersing them out into the ISM through those explosions. So the ISM is the interstellar medium, all of the gas and dust that lives between the stars, kind of in comparison to the CGM that Ed was talking about earlier. So what I've been doing is using simulations to study supernova explosions. So most of the supernovae that are observed these days take the form of just like bright spots in distant galaxies. Most of them are pretty far away. It's not often that you get one that is near enough to the Earth to be observed in detail and actually resolved with a telescope like this image I have on the left here. They're truly a once in a lifetime event if you're lucky. If you're a career astronomer for 50 years, you might get one, you might not. And this is actually, the picture on the left here is actually a fairly recent supernova explosion that happened in 1604. So if we want to study these sorts of things on human timescales and not risk being dead before you see one, then computer simulations are a really essential tool because they can happen on much more accessible human timescales. So what I'm working on is supernova simulations with a focus on nucleosynthesis. So the simulations we're doing are core collapse simulations in full 3D. We're not taking any shortcuts there. And we're using the hydrodynamics code SNSPH. And then after the fact, we're going back and doing a lot of post-processing to get nucleosynthetic values for more than 500 isotopes. We have this big network that allows us to predict all the yields that come out of this supernova simulation, going fairly high up the periodic table. So the emphasis of my project is looking at the effects of asymmetry on explosions. So they're not perfectly spherical, as let's just go to the next slide. As you can see in this collage here from the Chandra X-ray Observatory, supernovae are a varied bunch. This is a bunch of different supernova remnants that have been observed in the X-rays with Chandra, and they're messy. They're not all just perfectly spherical explosions. They tend to have a lot of different shapes. And scientific models, as a general rule, give us the best insights about reality when they emulate reality as closely as possible. And not a lot of work has been done in the supernova simulation community on how to quantify the effects that this kind of morphology of the explosion has on the yields. So that's what we're working on. Now, here's a quick list of the couple of models that I'm going to be briefly touching on today. We have a single progenitor star, which was evolved in the stellar evolution code Tycho. It started with a mass of 15 solar masses at solar metallicity, and the star was not rotating. And we're using a single progenitor star so that the different explosions that we're imposing on it can be the only thing that is possibly changing the yields of the explosion. And those asymmetries are going to be artificially imposed at the moment when core collapse happens in the star. So just to kind of quickly go through this list, we have a spherically symmetric model where we didn't impose anything on trying to make the model less symmetrical. That's kind of our control that we can compare everything else to. We have a bipolar model where the velocities of the material were rescaled so that the material toward the star's poles was going about twice the velocity of the stuff near the equator. So you wind up with an explosion that's preferentially toward the star's poles. We have a model that included a dynamic compact object, the neutron star at the center of it, that I unfortunately will not be able to talk about today, but that was a fairly recent paper from us that gave the compact object a nice, let's just say, extra freedom to move around than is usually the case in supernova simulations. And the one I'm going to be discussing today briefly is a model based on realistic three-dimensional convection from a 3D stellar model. So let me just move on to that slide. So this newest model that we're really excited about is a realistic treatment of a supernova shock moving through a turbulent stellar interior. Now, the stars that explode as supernovae are not, it's not something that they wake up one day and decide, hey, I'm just going to explode. It's a process that builds up to the explosion, and especially very massive stars over 20, 30 solar masses, they can be very turbulent inside when there's a lot of energy moving around and a lot of matter, and often they throw off tons of outer layers before they even explode. They're turbulent and troubled individuals. So what we did is we ran a 3D stellar evolution model for a fairly short period of time near the end of the star's life, right before core collapse, used the convection in that star to seed asymmetries in the model, and then we used that model to then explode. So it's the first supernova simulation of its kind. No one has done anything like this before because fully three-dimensional stellar evolution models are hugely computationally intensive. But we are excited to be presenting this. So let's get into just a few preliminary results from this. So here we're looking at renders of cross sections of a couple of these models where the brightness is indicating the abundance of oxygen. So this bright ring that you're seeing in both of them is the oxygen shell in the star that's being blown apart with all of those fluid instabilities. You can see these fingers that are from Raleigh-Taylor instabilities. And in the symmetric model, there's still some fluid instabilities that are happening, but it's at least the inside of the oxygen shell is reasonably spherical. Whereas by comparison, the convective velocity model, firstly, you can see that in this new model, the inner region is not nearly as spherical. You can see that the region outside the oxygen shell, whereas in the other model, it's just pitch black. There's basically no oxygen there. You can see that it's kind of this nice shade of orange that shows that there's been a lot more material mixed in there. And you can even see that in the sort of northeast corner here, that there's a section where there's a hole in the oxygen shell where material from the outside has been mixing with material from the inside. And the last thing I'm going to show is just a comparison of some of the yields from these simulations. So this plot requires a little bit of explanation, so if you'll bear with me, the horizontal axis that you're seeing is the proton number of each of the isotopes. So, there's nitrogen with that nice spike at a proton number of 7, and I've got a couple of other particularly strange ones that are labeled here. And the horizontal or the vertical axis is the abundance of these elements in the various models normalized to the symmetric model. So there's this horizontal line at 0, the blue that you can kind of see hiding in the background is the symmetric model, and then all of the other models are plotted relative to that on a log scale. So this red spike that you're seeing for nitrogen here that's going up beyond 2 is indicating that new convective velocity model is ultimately yielding more than 100 times the amount of nitrogen that the symmetric model was yielding. And we're seeing similar results for vanadium, manganese, and cobalt over here. And then there's a big deficiency in a lot of these elements, like copper and beyond. And this is, we're seeing, as you can see, the convective model is producing larger differences from the symmetric model than any of the other models. The bipolar model has a few differences, the kind of yellowish orange line here, and the biggest to date before this convective model was this dynamic compact object model, the gray line here. But we're really excited to continue exploring these results from the convective model and try to figure out why we're getting such huge differences. So just a quick summary of kind of where we hope to go from here. We're hoping to get these models published this year, but there's a lot of analysis that still has to happen. The simulation models need to be run, and then there's a lot of, even once they're run, they produce tens of gigabytes of output, and there's a lot of analysis that needs to happen before we can get some nice visuals and understand what's happening there. We're hoping that the final paper will include more of a deep exploration of some of the more important radioisotopes like titanium-44 and nickel-56, which are important probes of the whole supernova engine mechanism that explains kind of how they happen. And the preliminary results are suggesting that the natural convective asymmetries from the internals of a high mass star can strongly influence the supernova yields just as much as anything else, if not more. So just to summarize and finish up, we talked about how supernova nucleosynthesis created most of the atoms that make up the Earth and its whole biosphere. As Carl Sagan once said, "We are star stuff." Asymmetries in supernova explosions play an essential role in that long cosmic process. And we're excited to be publishing our set of models this year, in addition to a new state-of-the-art model of convective asymmetries. Thank you very much.
Great, thank you. And pretty much right on time. So we have time for a couple more questions. You guys all did great. We have time for a couple questions if anybody has any.
All right, shoot.
Here we go. Maitri has a question. Cool stuff. What kind of N-isotope ratios do you get with the last model? Nitrogen isotopes.
Nitrogen isotopes. So yeah, Maitri and a student of hers, Jack Schult, and I have kind of been working together on the consequences of these models for a lot of pre-solar grain work in meteorites. And I haven't had much of a chance to look at the exact ratios of all the nitrogen isotopes yet, but Maitri, I should definitely, as we look at this model a little bit more, and I'm doing some new calculations for you as well for some of the other models, I should definitely send some of this data over to you so that we can take a look at the nitrogen isotopes that could make a big difference.
All right. And Summoner has a comment on a question. Your first pictures, both Alison Lal and Ravi Sankrit got their PhDs at ASU.
Oh, cool.
So,
what was that? Was that the...
So fly the Sun Devil flag. And we got another question.
There we go. I think it's this one, the Crab Nebula image, which really cool.
And one more question here, and then we'll wrap up. Why, Addison Sherman asks, why only choose the 44 titanium and 56 nickel isotopes to focus on?
They aren't the only ones you can focus on. Like, for instance, some of the iron isotopes, and I know especially aluminum-26 is very important for people like Maitri who do meteoritics work. And we're definitely going to look at some of those as well. But titanium-44 and nickel-56 are particularly important for probing the supernova mechanism because they're high enough mass, close enough to iron, that they tend to come from deep within the star, and they get closer to the conditions of the core and that sort of thing. And also, both of them are radioactive, and they decay producing photons at energies that are really nice for observers. Like I know titanium-44 especially is like, if you have an X-ray telescope like Chandra, then you can catch a lot of emission from titanium-44, and you can actually make measurements of how much titanium-44 is in supernova remnants. And if we focus our analysis on titanium-44, then that allows us to compare our theoretical results to observations of actual supernova remnants.
All right, and I think with that, we'll wrap it up. So I just want to thank Ed and John and Greg. It takes a little bit of courage to volunteer to stand up and do one of these talks, and you guys all did a great job, just like all the students before you have done. So it's really awesome to see our graduate students step forward and give these presentations. So thank you very much. You guys were awesome, and thanks to everyone for coming, and we'll see you next week.